This is just a short video to finish off this problem. I've managed to get this set up and solved it down to these last two equations here, where I had n sine theta plus f cos theta equals ma, n cos theta minus f sine theta equals mg. And this is the car traveling at constant speed. And I looked at that and drew a blank for a minute, but here's how I solved it. And first thing I'll do is just reproduce those two equations right there, and then make note of the fact that the frictional force is mu sub s times n. And so we've got these two equations here that look a little bit inconvenient, but I can replace the f's with mu sub s n, and then I've got things in terms of n and other stuff. So it'll simplify by quite a bit. So the bottom equation there, when I plug the mu sub s n into that thing, it becomes n cos theta minus mu sub s n sine theta equals mg, and I can solve that for the normal force in terms of mg. And it looks a little bit scarier than it typically does. First thing I did was factor the n out of here and then divide it by what was left. Looks a little bit scary for a normal force, but that's okay. We can deal with that. Now I can take that expression for n and plug it into here. Again, I would replace the f with mu sub s n. So the first thing that happens is I replace f with mu sub s n. Then I can factor n out of these two terms on the left side and get that, and then take this expression for n and just plug it in right there. So it's just a bunch of algebra that I'm having to do here, and do that, and I end up with, I'm able to divide the m's out at this point because they show up proportional on both sides, and I get the acceleration in terms of g. Now, does this make sense? What if we had a flat surface and theta was 0? The sine theta terms would vanish. I'd get a equals mu sub s cos theta divided by cos theta times g. Well, the cos theta terms divide out, and I get a equals mu sub sg. We've run into that before for a maximum acceleration when you have static friction. And so it works when I go to that extreme of a slope of 0 on that banked curve. Okay, so let's continue a little bit farther with this. Now, I'll make use of the fact that our acceleration is centripetal. We've got v squared over r. And so we can solve this for v. What I would have done first is multiply out from underneath by r. So I've got rg, got this term, and then it's v squared, so I took a square root. So we've got that. And now we can finally plug in some numbers. First thing I wanted to do was simplify this term in the parentheses. And with theta equal to 5.0 degrees and mu sub s equals 0.68, I can simplify that down quite a bit. Just analyze the whole thing. I'm having to be real careful with plugging things into the calculator and with algebra, but I end up with 0.82 for that whole term. So under that radical I have 0.82 times the radius of curvature, 285 meters, g 9.81 meters per second squared, and I end up with a maximum speed of 48 meters per second, which happens to be about 107 miles an hour. So you can go pretty fast on this curve if it's banked that way without skidding. But don't drive like that. So there's the end of that problem. It wasn't as bad as I thought. I should have been able to finish that off. I just drew a blank there for a minute.